Hi, in this video, we're going to go over analysis of covariance. All right, so the big idea of analysis of covariance is that we have a linear regression situation where we have slope and we have categorical variables, but we're not interested in interaction. So what we're going to do, we're going to make the assumption that we don't have interaction, and we want to analyze the model from there. So we're saying that for different levels of that categorical variable, we have a constant slope. Or we could say that we have a constant slope, and but the intercept term raises or decreases our line of best fit, depending on what's going on. Now, there's going to be three possible situations. First one is where we're interested in the categorical variables like intercept effect, up and down, and the other one is going to be the overall slope. We might be interested in both, or maybe we're only interested in the intercepts effect of up and down, and we're treating the slope as a nuisance variable, or possibly we're interested in the slope and the categorical variable is a nuisance variable. And so it depends on the situation when we're in. And so we're either going to be interested in both the categorical variable and the independent continuous variable, or we could be in the situation where the categorical variable is a nuisance variable, and we're really interested in the slope of that continuous variable. Or we could be in the situation where the continuous variable is a nuisance variable, and we're interested in the categorical variable as an independent variable. And so it depends on what we're doing, what our analysis goals are, what our stakeholders are interested in. So just like any other situation where we're doing something like this with a mixture of ANCOVA and regression, we have assumptions. So first one is that we have normality of the residuals. We make the assumption that the residuals are normally distributed. We make the assumption that we have homogeneity of variance with respect to the categorical and the continuous independent variables. So for all levels of our independent variables, we have constant variance. And we're also making the assumption that we have homogeneity of the regression slope. And so here, what's going to end up happening is that for each different value of the categorical variable, we're going to have parallel lines. Now, we potentially will have inconsistent space vertically between the parallel lines, but we're making the assumption that we have the same slope every single time for all of the different levels of our categorical variable. And then, of course, just like with any other statistic situation, we're going to make the assumption that our residuals are independent. All right, so now, why would we choose this over just ANCOVA or regression? Well, analysis of covariance is going to have more statistical power than approaching this with only the categorical variable or only the slope for regression. By having these together, I can account for more variance in the dependent variable. And so basically, I'm just more likely to have something statistically significant, which means I have more power. Now, something that we need to consider is interaction. All right, so in this situation, we are making the assumption that we do not have interaction between our categorical variable, independent variable, and our continuous independent variable. And so maybe we'll run a hypothesis test before we reach that conclusion, or possibly from subject matter knowledge, or maybe we're in a situation where our stakeholders want to approach it as if it's true, even if it's maybe not quite right, to just have a simpler presentation, a simpler model to work with. And so analysis of covariance treats the independent variables as having an additive effect. Well, if we had an interaction model, it would in effect be a multiplicative aspect, because for interaction, I would have the additive effects that we just talked about, plus a multiplicative aspect between the different categories and the slope. And so the interaction model the effect of the continuous variable would differ across different levels of the categorical variable. And so if I believe that the slope of the continuous variable could change by levels of the categories, then I don't want to run analysis of covariance. I want a full interaction model. In general, statisticians prefer simpler models. So if we can, we would prefer the analysis of covariance model over the interaction model, just because interaction is just a little bit more complicated with that extra term. All right, so now I want to visualize using ggplot what we're talking about. And so here, what we've got, we have horsepower is an independent variable, and we can see that it's along the x-axis. Carburetor is a categorical variable for, actually, excuse me, it's ordinal for this one. So there's an order to it. And then miles per gallon is our dependent variable. And in analysis of covariance, we're making the assumption that we have these parallel lines. You notice that here's a regression line when carburetor is equal to 1. Here's a regression line when carburetor is 2 or 3. Here's the regression line when the carburetor is 4 or more. Now, in this fitting setup, we're finding the line of best fit, or the model of best fit, when we're making the assumption that there's exactly one value of the slope. Now, looking at this, you could see with this red that the red dots actually look quite a bit steeper than the actual red line. So maybe this is not the best model for the situation. Here, this is just not fictitious, but this is just an example for me to generate to show you. But just eyeballing it, I'm kind of worried that this is not the right model. Maybe I should have an interaction term. But let's say I'm in the hypothetical situation where my stakeholders want an analysis of covariance, or I believe from my analysis or my subject matter experts that analysis of covariance is the way to go, that we have a constant slope across all levels of the categorical variable, then the model here, as we have printed, would work out. Now, let's go ahead and compare this to a model with interaction. So a model with interaction, you'll notice that the red is much steeper here. The blue is, it is changed a little bit, but it's in the same ballpark. And the green has also changed. And so, visually, I might prefer the interaction model. So if I'm trying to decide on which one to go with, this gives me an indication visually of what I should do. All right, so now let's go ahead and run through an example using R. So I'm going to go through the model that I just showed you using ggplot. So this corresponds to the first one. Here is I'm making the assumption that the analysis of covariance hypothesis is correct, that we don't have interaction. And so just like any other model, I can fit it. And then, I can run the summary function. And this behaves a lot like a linear model from R, but not quite 100%. You notice that on the summary, I don't get any coefficients. Now, my analysis of variance, we get the same hypothesis test off of that if I drop it into ANCOVA. Now, for plotting, the output of analysis of covariance looks a lot like a linear model. There are 6 plots that come out just by the default of R. If I want all of them, I would put which equals 1 through 6. By default, if I did not specify that which command, what would end up happening is that R has 4 predetermined ones that it's going to run through and present. And now here, notice that the 3 most extreme always get labeled on every single plot when I'm using the default plotting function for a linear model in R. And so we see Maserati and Toyota Corolla and Lotus Europa. And so here, you might think that there might be a curve here, but if I can move 1 point, if I could add, delete, or move 1 point, you don't see a trend. If I was to take this Maserati dot and I moved it down here, then overall, visually, my eyes would kind of see a trend like this, and which contradicts the plot that I'm seeing. So I don't think I have a trend to be worried about here. There may be something going on. There's not enough data points for me to reach a firm conclusion. Now, for the normal QQ plot, to the left and center, that's looking pretty close to normal, but to the right, that's definitely deviating. So I conclude that my residuals are not normally distributed. Now, I might still proceed with the model depending on my situation, but this is something I definitely want to notice. Something I want to be honest about with my stakeholders if they go this deep into statistics. Now, with the Toyota and the Maserati, we see that again. Once again, Toyota Corolla and Maserati are there being plotted. The three most extreme always get labeled in these plots. And I feel like there's no trend to see off of this. Cook's distance, now this one is the most concerning of all the plots, in my opinion. Here you can see that the Cook's distance for the Maserati is pretty tall. Also, we're consistently seeing Maserati on the plots. So I have some concerns about it. Also, you'll notice that the Toyota Corolla is on every single plot also. Those two get labeled every single time. And so if I was doing this for work, I would go back, I would want to double check the data. Is the data correct? Is the data appropriate for my project? And I might want to remove it. So the Maserati, like if I didn't know anything else about the situation, what I would do, I would go in and I would actually omit that from the data set. The Toyota Corolla, I think that's close enough for the rest that it's okay. Remember that R always labels the most extreme three. And so Toyota Corolla is sticking out there, but it's not so far that I feel like it would warrant, removing it from the data set. Now here's our Cook's distance versus leverage. Now we can also do multivariate analysis of covariance. So instead of ANCOVA, it's MANCOVA. And so R will do this for us. Here, I just wanted to present the simplest case to warm us up for it and get you interested in it. And so analysis of covariance is a powerful statistical tool that can increase the precision of our analysis by adjusting for the variance accounted for by covariates. And this can increase the statistical power compared to running just regular old ANOVA. All right, well, that's all I've got for you. Life is short. Do math.